Hello everyone. All right, it is time for 8.6, where we are going to talk about molecular structure of acids and bases. Okay, so let's get right into this. We've been talking about strength of acids and bases and their conjugates, and so we need to talk about what exactly, why does a strong acid ionize completely? Like, what's up with that? Like, why does it do it? And then we have the weak acids that only ionize a little bit. So they only split apart just a certain amount of their hydrogen ions that they will lose. So number one, we have to think about which proton is being ionized and what other atom is it attached to. That's important. And then the stability of the conjugate base. So how stable is the conjugate base? And so maybe we should define stability of the conjugate base. So if the conjugate base, which is going to be negative, because if you remember, if you have HA, you're going to get an H plus and an A minus. So this is your acid and this is your conjugate base, right? So if your conjugate base is, for lack of a better word, okay with maintaining a negative charge because it has like a high electronegativity, then it's going to be a stable conjugate base. All right, but if it's not okay maintaining a negative charge because it doesn't have that high of an electronegativity, then it's not going to be a very stable conjugate base, and then it's going to try to react and rectify the problem. So that's what we're going to talk about. Okay, so first of all, go back here. We're going to talk about this first. So which protons are ionized? And then the rest of today we'll be talking about this. Okay, so when we see this is a very common acetic acid. All right, so we have acetic acid. The other way you could see it written would be like CH3COOH. So this is written like an ionic compound. This is written as an organic molecule. And in this particular unit, they like to draw these out more like organic molecules, even though it's not something that we teach in AP Chem, which is kind of a pain in the butt. But just understand that they're the same. Okay, so it's acetate. It also has another name, which AP does sometimes use, and we'll talk about that on the next slide. So we have this acetic acid molecule, and it looks like this. If you were to draw it, like, it's supposed to represent a 3D drawing, and you can tell that because of this and this right here. But you also have the same molecule here. So these are both acetic acid. Now, there are multiple hydrogens. There we go. There's multiple hydrogens on this particular molecule. There are 4 of them. There's 3 that belong to the acetate ion, and then there's the one that makes it an acid. So these acetate ion, these 3 hydrogens are part of the acetate ion. This hydrogen is the acidic proton. Okay, so hydrogens that are attached to atoms with a large electronegativity are your acidic protons. So over here, hydrogen's attached to oxygen. That makes him rather acidic. Think about the periodic table. Top right-hand side are your most electronegative atoms. Ignore group 8 because their relative electronegativities are non-existent. But fluorine is the most electronegative atom on the periodic table. Oxygen is right there. He's right there next to him. And so oxygen's pretty electronegative. Carbon, not so much. So carbon's not considered a highly electronegative atom. So these 3 hydrogens that are attached to him are going to be attached to him. This molecule's not going to be willing to give up those hydrogens, these 3 hydrogens here in particular, because carbon's not really going to be okay with maintaining a lone pair of electrons. He wants to have 4 bonds, 8 electrons in the sense of 4 bonds, not a lone pair attached to him. That's not stable for him. And so that would create an unstable conjugate base. So, and when this acid donates this proton, and you get the H plus over here, this is the conjugate base. And so that's just not going to work out very well if carbon is the one that's having to maintain the negative charge. But if we lose this hydrogen over here, then that's okay because oxygen's maintaining the negative charge. And so we would say that that would be a more stable conjugate base. Okay? Now, so questions about this pop up a lot. So these are your halides, which is group 7A off the periodic table. So you have fluorine at the top and then chlorine, bromine, and iodine. And so we know that these three are strong acids. So hydrochloric, hydrobromic, and hydroiodic acids are really strong. And you can see that these are the pKa values. So remember, the pKa was the negative log of the Ka. So if you have a low pKa, that means you have a high Ka. And the higher your Ka, the stronger the acid. So the higher your Ka value, the stronger the acid. So you notice that these pKa's for I and Br and Cl are really low. They're negative. And so since they're really low, they're actually negative values. These are really high Ka values. They're super strong. They're like off the charts, crazy strong. And then you have fluorine over here that, I mean, it is a huge difference between fluorine and the rest of them. So yes, fluorine is small. Small is part of it for sure. Size is definitely part of this argument, but probably a more valid and acceptable response would be making an electronegativity argument. Fluorine is the most electronegative element on the periodic table. All right, so he's going to hold on to his H a lot more strongly than I, Br, and Cl. Sorry. So he's going to hold on to that H a lot more strongly because he's more electronegative. And so just kind of look into or think about what's going on with electronegativity. Not just size. Size is part of it, but it's not the all end all answer. Okay, so for the rest of this, we're going to talk about the conjugate stability. Now, these two elements these two molecules are very similar. So we have acetic acid. It's a C2H3O2. That's the acetate ion with the H at the end. And the H is attached to this oxygen right here. And then we have ethanol, which is not considered an acid, but it's also, notice, it has two carbons, just like this one does. And the only difference between these two is what's happening here. Other than that, they're the same molecule, right? The CH3 on the left-hand side, they have a second carbon, there's an OH group. So it's very common to compare them. But just so you know, I told you there was another name for the acetate ion, and then the acetic acid name for this molecule. It's also known as ethanoic acid. So organic molecules are carbons and hydrogens, and they name them based upon the number of carbons that are present. The prefix eth is associated with two carbons. That's where the eth is coming from. So ethanol, so it's two carbons, and all means it has an OH, and it functions as an alcohol group. Whereas acetic acid or ethanoic acid means it has two carbons, but it is a carboxylic acid, which has a COOH group. Now, we do not get into organic chemistry in AP. We used to do a little bit of nomenclature and drawing. They've taken it away, but they like to interject it into the class because they can, and they sometimes freak kids out, but don't let them. And I will say they have gotten better about using the names like ethanoic acid, which you've not heard before today. But then they would show you the molecule or tell you what it is. So they're doing better about letting you know. So don't panic, just read through the problem. They love to put stuff on there that you've never heard of before because it freaks you out, and then you act like you can't do the chemistry when you can. So calm down, okay? All right, so both ethanol and ethanoic acid have very, very polar OH bond. So it is right here. That's a polar bond for sure. All right, so they both have that, but acetic acid will behave like an acid. Look at that Ka value. I mean, it's a weak acid, but that's not a terrible Ka value. That's on the higher range of weak acids, okay? 10 to the -5 is not that bad. But ethanoic acid, 10 to the -16. 10 to the -16, this little dude, he's not even considered an acid. This guy is not going to act like an acid at all. Why? What's the deal? What is the deal? Why does that make such a big difference? And it's going to go directly to the fact that the conjugate stability. Now, the fact that they both have a hydrogen to an oxygen, you can't make the argument about the first thing that we talked about, which is what type of proton is it? Because they both have technically an acidic proton, because they both have a proton that's attached to an electronegative atom, like oxygen. So they both have that, so check, no problem. But then the second part is the stability of the conjugate. So when it ditches at those acidic protons, if it were to do that, then what's it going to look like? And so that's what our next slide shows us. Okay, so this is acetate. So the acetate ion. So there was a hydrogen here and a hydrogen, well, it moves around because there's resonance in the structure. So, but there's a hydrogen here. It was attached to this oxygen, and then there was a hydrogen attached to this oxygen. Okay. All right, so just so you know what you're looking at, we're looking at both of them. So this is the conjugate base, and this is the conjugate base of its acid. Now the difference is due to the ability, and for this particular molecule, and you have to look at each one because there's different reasons why they're more stable. There's not always a one and done answer, but take a look and see. This one in particular has resonance. So if you have this scenario, then the lone pair is going to move back and forth between these two oxygens. And so it's going to go back and forth and back and forth and back and forth. Well, that resonance creates a stability. Why? Okay, well, this goes back into formal charge even. So you could even go and make a formal charge argument if you remember how to do that. If not, let's review real quick. So formal charge, we take our valence electrons, and then let's just do it. We'll work through it. Oxygen. Oxygen's in group 6. It has, see if I can write up above. I can't. It has 6 valence electrons. So this first oxygen that I have circled, or this would be oxygen number 1, he has 4 lone pairs. So he has 4 electrons that are solely, he has 4 lone pairs. He has 2 lone pairs, 4 electrons that belong to him exclusively. And they are 1, 2, 3, 4. So I'm going to subtract those 4. Then he has 4 electrons touching him in a bond, but he has to share his bond. He only has half of it, so he only has a dot from this one and a dot from this one, so -2. So he only has 2 electrons touching from the bond. There's a total of 4 there, but he has to share them with carbon, so carbon gets 2 of them and oxygen gets 2 of them. That's where the 2 comes from, and that equals 0. And if you remember, we want a formal charge close to 0 if at all possible. All right, this one right here, this guy has 6 valence electrons minus 6 lone pairs that are touching him, minus 1 that's in the bond, so he's -1. All right, so this was oxygen number 2. So this was number 1, and this was number 2. All right, this guy over here, he is just like number 2 electron. He is a formal charge of -1. Now, we could do the whole molecule in terms of doing the formal charge for the whole thing, but here's the deal. What I want you to recognize is that this one's formal charge, number 1's formal charge is 0. Number 2's formal charge is -1. They're going to share that. So because of resonance, they're going to share that. And so that is going to actually reduce it down to about an average of -0.5 formal charge. And you want to be as close to 0 as possible to be considered stable and satisfied. All right, so on average, these oxygen are averaging 0.5. This guy has nobody to share the negative charge with. The carbon's definitely not going to take any of it. Not going to do anything with it. So the negative 0.5 is closer to 0 than the -1. So this guy, if he were just acting as a conjugate base, he's more stable than this one. So the acetate ion or the ethanoate ion is more stable than the ethoxide ion that you see over here, which came from the ethanol. So that resonance creates stability in the molecule. And the more stable you are, then that's a good thing. So that means that you will react and behave like a conjugate base. If you're not stable, then what's going to happen is, and I'll come back to that one. All right, if you're not stable, so this is that same molecule right here. This was the ethanol after he lost his proton, and he has formal charge of -1. The weakness of ethanol as an acid is because his conjugate base, this ethoxide ion, is considered a strong base. Why is he a strong base? Because he's not a stable conjugate. This is a conjugate base and he is not stable. So if he's not stable, he's strong. Why? If he's not stable, he has to do something to correct it to make him stable. So what is he going to do? He is going to be doing everything he can to accept a proton. Everything in his power. He is going to be ripping apart those water molecules and taking them away. All right, so he actually becomes a strong base. He's going to be a proton acceptor in order to stabilize this molecule. Where acetate is just floating around in there and he's like, whatever. He's okay. So will acetate react with water? Yes, of course. Is it going to react with water a lot? No. This molecule here, because he's not as stable, is going to react with water more than this molecule because he is a stable conjugate base. They're both conjugate bases. The acetate is more stable. Why? In this case, because of resonance. Okay? Now, well, I knew you were fast looking. You already saw the answer, but that's okay. All right, so which of the following is the strongest acid? Well, hopefully you know one of these is a for sure strong acid because you know your strong acids list. But the more oxygens that you have present in a molecule, the more stable your molecule. Okay, so this guy over here on the right, he has 4 oxygens. Typically, oxyacids, the more oxygens you have, the stronger your acid. So the more oxygens in your oxyacid, the stronger your acid is. So this is perchloric acid, very strong. Very, very, very strong. So this guy's very strong compared to like this guy over here. He's a pretty weak acid. And so you're increasing this electron density over here. And when you're increasing this electron density in this molecule because you're adding in these oxygens, and these oxygens are very electronegative. So take a look at what's happening. This bond stays the same, right? I've got 1 oxygen here. I now have 2 oxygens here. I now have 3 oxygens here. So what's happening is you're adding these oxygens, which are pretty electronegative. And what they're doing is these oxygens, this electronegative region, are pulling the electrons this way. The electrons are getting pulled closer to them. It's a big electron cloud, and those oxygens are highly electronegative, and they're pulling the electrons closer to them. And when they do that, this bond, well, crud. This hydrogen-oxygen bond is weakened. And because it's weakened, it's easier to remove that hydrogen. Okay, so that's what's going on. You have a massive electron cloud, and we're dealing with oxyacids, so that means they have oxygens added to them. And these oxygens, look at what do these molecules have in common? They have in common this. And so every time I add an oxygen, I'm adding a pretty high electronegativity atom, and it's pulling the electrons away. So this one over here is pulling the electrons more because there's 3 of them. And then this one's pulling them the second most, and then this one's pulling them the least out of these 3. And then, that's really what's happening. And then there's going to be the one that just looks like this. They didn't put that one on there, but that would be the weakest because there's not any oxygens pulling, any additional oxygens pulling, and then this you have that guy who's going to hang on. All right, so now those are your oxy acids. We have our answer. We did that one. Okay, so now let's talk about another thing that can make your conjugate stable. So number one, strong versus weak acid depends on who the proton is. Gotta have an acidic proton. Number one, you are acidic if you are a hydrogen that's attached to an electronegative atom. That's number one, highly electronegative atom. All right, number two, stability of your conjugate base. So we just talked about a couple of things where we've discussed stability of the conjugate base when I have resonance. That's a big one. What oxyacids do, adding all those oxygens to an oxyacid will do something to pull the electrons closer to those oxygens, which weakens that OH bond. That's your acidic proton. So it's easier to give it up. And that also is a very stable conjugate base. Why? Because it has all that electronegativity. So it's able to hold on to that negative charge. And it's totally satisfied maintaining itself, holding on to a negative charge. Now, in this particular case, let's start on the right-hand side and work our way backward because it might be easier to see what the heck is going on here. So we have our acetic acid over here on the right-hand side. It looks like this. Okay, so we have the C, double bond O, and an OH. This is my acidic proton over here because that's the H that's attached to the highly electronegative atom. And this has 3 hydrogens to this carbon down here. Now, this was copy and pasted out of a textbook, and there's a little boo-boo in their printing because there's supposed to be a C right in between the Cl and that H2. I don't know what happened to it. But again, just the way it goes. All right, so it's still the C, OOH, and then I have a C in the middle. And instead of 3 hydrogens, there's only 2, and they added 1 chlorine, so it's monochloro. This is getting into organic nomenclature, which you don't know, and that's okay. All right, and then on this one, I have the C, and then the COOH. The acidic proton is here, just like it was here. But instead of 3 hydrogens, I now only have 1, and I have 2 chlorines, because it's a dichloro. And then this last one, they got rid of all 3 of the hydrogens on the end, and I have replaced them all with chlorines. So there's something called an inductive effect. Inductive means if I do something here, it has an effect somewhere else in my area. So in my area, inductive effects are things that influence other things. So it's like an influencer, kind of. So if you have the presence of a nearby electronegative atom, so the electronegative atom in this case they're talking about is chlorine. So chlorine is not directly affected by where these hydrogens are. It's not directly bonded to, I'm trying to circle over here, it's not letting me. The chlorine is not directly attached to where the acidic proton is, but it's in the area, it's in the molecule, it's just on the other side of the molecule. So what happens is this addition of this chlorine, who is an electronegative atom, just like oxygen is, helps to share in that negative charge, just like it did on the oxyacids, which increases the stability of the conjugate. So it's a little different in the oxyacids in that sense, but it's still an electronegative atom, but it increases the stability of the conjugate. So it makes it easier for this molecule to release that H+. So this is referred to as the inductive effect. So it's not directly, it's a couple atoms away within the molecule, but what's happening is it's still going to pull the electrons just like that oxyacid does. And so it's going to make it a lot easier to release that hydrogen because it's going to weaken that OH bond. So which bond? This one, this one, this one, this one. It'll weaken it. Why? Because I'm adding all these electronegative atoms in my molecule, not as closely related as the oxyacids were because it was right on the junction atom, but it's a little further away, but it still works the same way. And when this happens, the more electronegative your conjugate base is, the more stable it is in maintaining that negative charge. So if you look at these Ka values, now these aren't pKa's, these are Kas. So the higher the Ka value, the stronger the acid. And so our regular acetic acid is 10 to the negative 5. Okay, it's a weak acid, so that's not terrible. But when I take one of those hydrogens away and I add a chlorine, go back, there we go, and add a chlorine, look at that, 10 to the negative 3. So that 10 to the negative 3, that is a stronger acid than the acetic acid. And then take a hydrogen away and add another one, 10 to the negative 2. That's now stronger. Why? Because I added another electronegative atom. Then add another chlorine and take off another hydrogen, 10 to the negative 1. This dude's getting mighty darn close to being pretty darn strong. So what's happening? It's very similar to this slide. No, this slide. But these additional oxygens are much, much closer to what's happening. So they're definitely pulling on the electrons from this bond and weakening that oxygen-hydrogen bond. And they also create a stable conjugate. But the same thing is true here. So every time I throw in a more electronegative atom, 1 chlorine, 2 chlorines, or 3, it's pulling the electrons away from that hydrogen-oxygen bond, so it weakens this bond. And when it weakens that bond, what's remaining is that it has to maintain that negative charge. So we've already talked about acetate can maintain its negative charge. We said that compared to like ethanol. But this one can maintain the negative charge better than this one can. Because it's more stable, because it's a more electronegative atom, so it can maintain that negative charge better. Okay? So that's kind of tough. I gotcha. I understand. Okay, so, and this is where I mentioned earlier about size is a thing, but don't get too hung up on it. When you're making an argument in AP, really focus on the electronegativity in terms of the acid strength. So general acid strength increases with more electronegative atoms when they are involved in the structure. So for example, we have our HOCl. So all of these are an oxy acid, but they just have one oxygen. So I have HOCl, HOBr, and HOI. And if you take a look, they have our electronegativity values here. And then I have my pKa's. Now remember, the lower the pKa, the higher the Ka, therefore the stronger the acid. Okay, so that means that HOCl has the lowest pKa out of these three. So out of these three, it's the strongest acid. So it's more acidic than HOBr and HOI. Why? Well, because chlorine, electronegativity of the X being the halide, because that's what's different between these three acids, is which halide is it. So the Cl is more electronegative than either the Br or the I. So that OH is more likely to give up its proton, because when it does give up its proton, you're going to end up with OCl minus, OBr minus, and OI minus. Okay? This guy has a higher electronegativity. So because he has a higher electronegativity, he's able to maintain that negative charge. So that makes him stable. It's all about stability. It's all about stability, you guys. Okay. Now, inductive effect makes bases weaker. So that inductive effect, the adding of a highly electronegative atom, will make your base weaker. So over here, it says, while the inductive effect stabilizes your acids and the conjugate acid, it makes a base less likely to accept a proton. Why? Because it's satisfied having its negative charge. Why would it need to add a proton? It's okay with how it's doing. So remember, the higher the pKb, the lower the Kb, so that means the weaker the base. So if you take a look at these pKb values right here, and what are these? These are NH3 over here on the right. That's ammonia, very common weak base. He has a low pKb, which means he has a high Kb. And then this guy right here, he's an amine because he's got a nitrogen, and he had one bromine replaced that hydrogen. So he's bromamine. Okay. And he has a higher pKb. So the higher the pKb, the weaker the base. The higher the pKb, the weaker the base. So this is a weaker base. This is a weak base, for sure. But this one is weaker. Why? Well, I threw in this very more electronegative element than a hydrogen. So this bromine is more electronegative, and so it was going to weaken my base. Because he's very stable, if he is to maintain his lone pair right here, which is negative. It's not a negative charge, but they're negative. Doesn't necessarily need a proton to come in and do anything. They're less likely to accept a proton. This molecule over here is a lot more willing to accept a proton than this one. Why? Because he has the addition of this electronegative atom. So it's the inductive effect, okay? It's pulling the electrons closer to him, pulling them closer to the bromine. That means there's less effect on that one side of the nitrogen. It's just not going to attract anyone. Okay, so this is AP at its best, giving you a really organic chemistry drawing of a molecule, not just first year chem. Okay, I'm going to show you what you're looking at, explain it in just a second. So how do you account for the difference in the pKa of the acetic acid, which is the one that's on the left, and the fluoroacetic acid, which is the one that's on the right? Okay, now if you were looking at this and you had no idea, how would you know which one was which? Well, you've got the one with the F in it, it's fluoro, and so that's the one with the F. Okay, so first things first, let's talk through what you're seeing. So chemists are lazy, ultimately. That's what they don't want to draw a bunch of stuff. And lots of molecules are ginormous, and so they don't want to draw it all out. And so here's the deal. They don't draw the carbons or the hydrogens. And the end points, so here, and junction points, here, are where you will find a carbon. So that's this notation. So there's a carbon here, and there's a carbon here. They also do not draw hydrogen. So they only draw other things that are attached to them, like fluorine, nitrogen, oxygen, hydrogen. They don't show hydrogens unless they're attached to something other than a carbon, I should say. If they're attached to an oxygen, they will draw it. If it's attached to a nitrogen, they will draw it. But if it's attached to just a carbon, they don't. So what are we actually looking at? Well, this first one is a CH3. C, double bond O, O, H. And then there's lone pairs on the oxygens. All right, this fluorine, the fluoroacetic acid, is you have a fluorine to a carbon, to another carbon, that's a double bond oxygen, to an oxygen, to a hydrogen. And then they fill in the lone pairs, but they're so lazy and they don't want to do all the drawing of the structure. And so these are what you're looking at. So if you were to have drawn these with me, you would have drawn what we just wrote in red. But this is how they write it as a shortcut, so that's what that means. Okay, so now that we kind of know what we're looking at, they're both these carboxylic acids, which is something that you don't know because you don't know functional groups anymore. But that's the COOH that we have. But how can you account for the difference? They both have two carbons. How can you account for the difference in the pKa? All right, the lower the pKa, the higher the Ka. So this first one has a pKa of 4.76, and this one has a pKa of 2.59. All right, the lower the pKa, the higher the Ka. So the higher the Ka. So the one on the right has a higher Ka value. The higher the Ka value, the stronger your acid. So I'll put, if I can fit it on here. Talk yourself through it. Lower the pKa, the higher the Ka. The higher the Ka, the higher or the stronger the acid. So that means that the fluoroacetic acid is stronger than regular acetic acid. Okay, why? Clearly it's got something to do with the F, right? because they have the same number of carbons. They're both a COOH group. They have all of that. They both have an acidic proton. It's this one. Okay, so what's the deal with F? What do we know about F? He's very electronegative. He's the most electronegative element that we have on the periodic table. So what is he doing? Well, fluorine's very electronegative, right? So he's pulling all the electrons towards him. He's pulling them towards him. And when he pulls the electrons toward him, it weakens this OH bond. This OH bond will be weakened. And then that hydrogen is much easier to escape. If the OH bond is weak, then that hydrogen is going to escape. It's gone. It's out of here. So the more electronegative is the inductive effect. So that electronegative atom is added in there instead of a hydrogen. It pulls the electrons away from everything and towards itself. And when it does that, it weakens that OH bond. That hydrogen's much more willing to leave. And the conjugate base that it leaves behind is carrying a negative charge, right? So for this one, you would have acetate, C2H3O2, which is going to carry a negative charge, and it'll do it. And then this one would be C2FH2O2. I think I got it right. So that would be this guy that's left behind. Well, this one's going to maintain that negative charge better than this one. Why? Because he has the electronegative fluorine in there. And so more electronegative you are, the more the ability for you to be able to hang on to that negative charge and be totally satisfied. Okay, so I know that's tough. I understand. That's not fun. But what I want you to do is think about that. There's a lot of thinking in that one. There's not math. So those of you that don't like the math, there you go. Here's you a non-math acid-base section.